So segment 3 of chapter 3. All right, so we left off looking at the strategy for determining empirical formulas. And we went through what the steps are. They're going to determine the mass in grams of each element. We're going to convert those masses into moles. And then we're going to divide all the quantities by the smallest number of moles, and that'll give us the smallest ratio of moles. We'll convert any of those non-integers into integers. Excuse me. And if we have a equivalent of a fraction, that will multiply through by the denominator of the fraction. Otherwise, we'll simply round to the nearest integer. And then I posed the problem where we had a sample of a compound. We know how much carbon was there, hydrogen and nitrogen. And then I realized that we were like 27 minutes and said, okay, let's stop here. So let's pick up from there. Step 1, we're going to calculate the moles of each of our substances. So we're going to start with those carbon, grams. We have 0.4470. We're going to get our mass from the periodic table. We divide through, and it gives us 3.722 times 10 to the negative 3. Now we're going to do the same thing for hydrogen. We're going to take our mass of hydrogen, divide by our periodic table value, and we have 1.860 times 10 to the negative 2. And then last but not least, we'll do the same thing for nitrogen, and that gives us our moles of nitrogen. So now we've gotten everybody into moles, and now we're going to look at the smallest value. So selecting the smallest, we're going to have 3.722 times 10 to the negative 3 moles. And so that was for the carbon. And so we're going to divide that through, and we're going to get 1. So the mole ratio then tells us we have 1 carbon. Now we'll do the same thing for hydrogen. We have 1.860 times 10 to the negative 2. We'll divide that by our moles of carbon. That gives us 4.997. And then we'll do that for nitrogen. Nitrogen, we get 3.723 divided by 3.722, and that's going to be roughly 1. So for our integer ratio then, we have 1 to 5 to 1. All right, now what we're going to do is divide all numbers of moles by the smallest one. That's going to give us CH5N. Right? So that's going to be our empirical formula. Easy peasy lemon squeezy. Now you might have to play that back a couple of times. I know it seems like it was going to be really, really complex, and then there's a lot of moles flying all over the place, and so you might just need to go back and look at it a couple more times. Once you get the hang of it though, you'll see that it's fairly simple, right? We'll take our masses, use the masses to figure out moles, then figure out mole ratios, and then round to the nearest integers, and then reduce that down so that it's our empirical formula. All right, so empirical formula for mass data. One of the compounds of iron and oxygen, black iron oxide, occurs naturally in the mineral magnetite. I can't pronounce that. When a 2.448 gram sample was analyzed, it was found to have 1.771 grams of iron and 0.677 grams of oxygen. Calculate the empirical formula of this compound. So the things we'll need, we know moles of iron, periodic table. We know moles of oxygen from the periodic table. Now we're going to find the moles of each element, then find the ratio of those moles. So we'll calculate the moles of each substance. So we have 1.771 grams of iron. We'll divide that by our molar mass. That gives us moles of iron. We'll do the same thing for the oxygen in the sample. That gives us moles of oxygen. Now we look at which number is the smallest, which is going to be the iron. That means we're going to get 1 iron. For the oxygen, we're going to get 0.0423, and that's going to give us 1.33. Now notice here we have the 0.33. Well, that's going to be the same equivalence as a fraction. So we're going to multiply it by 3. And that's going to give us 3.99. Well, if we multiply the oxygen by 3, then guess what else we have to do? Right. We need to multiply the iron by 3. So now we can see we have 3 irons and 3.99 oxygens. Or we can say we have 1 to 1.33, which is going to give us 3 and 3.99, or 3 and 4, right? So our empirical formula then would be Fe3O4. Now, empirical formula from percent composition. New compounds are characterized by elemental analysis, from which the percentage composition can be obtained. You'll use that percentage composition data to calculate your empirical formula. Now you must convert your percentage composition to grams. And so the way we're going to do that is we're going to assume we have a 100-gram sample. This makes it convenient, right? If the sum of the percent composition has to equal 100%, then the sum of our masses will have to equal 100 grams. So I'm going to send a sample out, and they're going to send back the data. And they're going to tell us we have 43.64% phosphorus, 56.36% oxygen. If the molar mass was determined to be 283.9, what is the molecular formula? So first we're going to assume we have 100 grams of sample. That means we have 43.64 grams of phosphorus and 56.36 grams of oxygen. We know the molar mass for phosphorus is going to be from the periodic table, 30.97. For oxygen, it's going to be 16. We're going to calculate how many moles of phosphorus we have. That's going to give us 1.409. Then we're going to calculate how many moles of oxygen we have. That's going to give us 3.523. Now we're going to divide by our smallest number of moles. So it's just like we did before. Phosphorus here was our smallest, so that's going to give us 1. And then we're going to take our 3.523 and divide that by the phosphorus moles. That gives us 2.5. Multiply to get your integers. We know we're going to multiply by 2 because we have a 0.5. So that's going to give us 5 oxygens and 2 phosphorus. Our formula then, empirical formula, is P2O5. Now our last thing is empirical formulas from indirect analysis. So in practice, compounds are not broken down into elements but are changed into other compounds whose formula is known. The most common here is the combustion analysis. So we're going to take our organic compound, we're going to combust it, we're going to burn it. So if it contains carbon, hydrogen, and oxygen, it can be burned completely in pure oxygen gas. Your only products will be carbon dioxide and water. We can then use scrubbers to catch them and figure out how much carbon dioxide was there and how much water is there. So for instance, the combustion of methanol, CH3OH, it's going to give us plus the 3 oxygens to give 2 CO2 and 4 water. Now the way this works is we're going to take our sample, we're going to put it in a glass tube, and then we're going to pump oxygen in and set it on fire. Then we're going to have an absorber that's going to grab all the water, and then we're going to have a scrubber that's going to grab all the carbon dioxide, and then any unused oxygen is going to go out. Now modern changes up a little bit, right? So here we're going to put our oxygen in. We're going to have our oxidation component, a reduction component. Your products are going to come down here and get cut in the column, and then through a detector, and then we're going to be able to detect what's there, right? So classically, we're scrubbing the water, scrubbing the carbon dioxide. Now we're pretty much doing the same thing here, except now we're letting the computer take care of it, and we're going to run it through a column. The column's going to slow things down so different things come off at different times, and the detector is going to detect them when they come off and then tell us how much is there. Then we'll get a printout, and that printout, based upon what's under the peak, will give us the percentage of what's there. Now carbon dioxide and water are separated and weighed separately, right? So all carbon that went into our system ended up as CO2. That's why it had to be pure oxygen, and that way we force it into complete combustion. All hydrogen is going to end up as H2O. So the mass of the carbon then is derived from the amount of CO2 that's in the samples. We'll do that 3-step process where we're going to take our mass of CO2, convert that into moles of CO2, convert that to moles of C, and then finally we'll have our mass for our carbon. For the hydrogen, it's the same concept, but we're going to be looking at the water. So now we're going to take the mass of water, convert that to moles of water, then moles of water to moles of hydrogen, finally moles of hydrogen to mass of hydrogen. The mass of oxygen is going to be obtained by difference. Okay, so the mass of oxygen will equal the mass sample minus the masses of the carbon and the hydrogen that we already calculated. So the combustion of a 5.217 gram sample of a compound in pure oxygen gave these masses. Calculate the empirical formula of the compound. So again, you can see all of our carbon went to CO2. All of our hydrogen is going to go to water. So the first thing we'll do is calculate the mass of carbon from the mass of our CO2. Remember, it's a three-step process. It's always a three-step process. Mass to mole, mole to mole, mole to mass. So we're going to take 7.406 grams of CO2. That came from the scrubber itself. We're going to convert that to moles of CO2. So there's my formula mass for my CO2. Then we're going to convert that to moles of carbon. This relationship is coming from there's one carbon in the CO2. So for every 1 mole of CO2, we get 1 mole of carbon. And then last but not least, we'll multiply by the periodic table. We run that through our calculator and we get 2.021 grams of carbon. All right. Now we're going to do the same process, but we're going to do it for hydrogen going to the water. So the mass of water to the moles of water to moles of hydrogen, mass of hydrogen. So now we'll start with the 4.512 grams of water, divide that by the molar mass of water, 2 hydrogens for every 1 mole of water, and then finally multiply by the periodic table for hydrogen. That gives us half a gram of hydrogen. Now last but not least, we're going to calculate the mass of the oxygen from the difference. We know that the 5.217 gram sample is composed of 2 grams of carbon and half a gram of hydrogen. That means 2.691 grams of oxygen have to be in the sample. So we can fill these tables in now. We know we have masses, 2.021 grams of carbon, 0.5049 grams of hydrogen, and 2.691 grams of oxygen. Now we'll calculate the mole for each element. So now it's just like it was in the last two problems. For the moles of carbon, we'll take the 2.021, divide by the periodic table value, and that gives us 0.1683 moles of carbon. For moles of hydrogen, same process, that gives us 0.5009 moles of hydrogen. For oxygen, we end up with 0.1682 moles of oxygen. Now, which one's the smallest? All right, so for the oxygen, we're going to put that in. That's going to give us 1 carbon, 2.97 hydrogen, and 1 oxygen. Now, because all of our values are close to integers, we'll simply round. And so our empirical formula then is CH3O. Phew, seems like a lot, I know, right? It just takes practice. You can go through these a few times on the video. Eventually, you'll get it down. Your turn. The combustion of a 13.660 gram sample of a compound of carbon, hydrogen, and sulfur, and pure oxygen gave these values. Calculate the empirical formula of the compound. So I'll pause here. All right, so your answer is C. How did you do? All right, let's take a look at the solution. So again, first thing we'll do is calculate the mass of carbon from the mass of CO2. There's our three-step process. We're going to take the 19.352 grams of CO2, divide by the molar mass of CO2. The mole-to-mole relationship is 1:1, and then we'll multiply by 12 from the periodic table. Grams of CO2 will cancel out, moles of CO2 will cancel out, moles of carbon will cancel out, and we'll be left with 5.281 grams of carbon. Next, we'll calculate the mass of the hydrogen from water. Same three-step process, but using water and hydrogen. So we'll go from mass of water, divide by the molar mass of water, that gives us moles of water. The moles of water to the moles of hydrogen is 2:1 based on the chemical formula. And last but not least, we'll use our periodic table to get our mass of hydrogen from moles of hydrogen. And that gives us 1.330 grams of hydrogen. So we know the mass of the carbon, and we know the mass of the hydrogen. Now we'll calculate the difference for the sulfur, just like we did with the oxygen. So we'll take 13.66 grams for our sample, minus the 5 grams of carbon, the 1 gram of hydrogen, means we have 7 grams of sulfur. Now we'll calculate our moles. So we have 0.4497 moles of carbon. Do the same thing for the hydrogen. We get 1.319 moles of hydrogen. Then for the sulfur, we'll use the 7 grams, and we get 0.2198 moles of sulfur. Now that we have our molar values, we can set it up. We can see that we can set up the ratios here. Sulfur, oh, that's a typo, right? That should be sulfur, not oxygen. All right, they carried the right number through though. So we have 2198. And again, don't get confused here. This is a typo. That should be sulfur, not oxygen. We'll do our mole to mole ratio. And so we're still going to divide by the number. Don't worry about the formula. So again, this should be S, not O. We blame the grad students for that one. There are our whole number ratios, our integer numbers ratios. We have 2.03 to 6 to 1. Because all of them are close, we get C2H6S. I think it's funny that they got it right in the final end, but they didn't fix it up here with the S's. All right. So determining molecular formulas, what we'll need is the empirical formula. So we'll accepted formula unit for ionic compounds, and of course we have molecular formulas are the preferred for molecular compounds. So in some cases, molecular empirical formulas can be the same. So we can have a molecular formula whose lowest common values, which is the empirical formula, are the same. Now, when they're different, the subscripts of molecular formulas are integer multiples of those in the empirical formula. So in other words, if your empirical formula was AXBY, then your molecular formula will simply be N times X and N times Y. So how do we determine the molecular formula then? Well, you'll need to know the molecular mass and the empirical formula. So calculate the ratio of molecular mass to mass predicted by the empirical formula. Hopefully that puppy in the background is not being too obnoxious for you. So, and then the multiplier will be the molecular mass divided by the empirical formula mass. So for instance, let's look at glucose. We know that the molar mass for glucose is 180.16. We know the empirical formula is CH2O. So what we'll do then is we'll figure out the mass for the empirical formula. So we'll take carbon as 12, hydrogen is 1.01, oxygen is 16, and that gives us 30.03. Now to figure out what the multiplier is, we'll take the molecular mass, the 180, and divide it by the empirical mass, 30.03, and that gives us 6. Then we simply just multiply our empirical formula by 6, and so we get C6H12O6. So the difference in determining this versus what we've been doing is I would have to then add in the molecular mass of the compound is. That way, once you have the empirical formula, you can then use the molar mass that I've given you to calculate what the actual formula should be. Let's look at a problem. The empirical formula of a compound containing phosphorus and oxygen was found to be P2O5. So that's what we had been doing for the first 15 minutes of this segment. If the molar mass is determined to be 283.9, that's a different analysis that they're going to give us that data from. What is the molecular formula? So remember, N is the multiplier for the molecular formula. We're going to take the molecular mass that they've provided and divide by the empirical mass. So all we have to do then is calculate the empirical mass from our empirical formula that we've already solved. So for P2O5, that's going to be 141.94. Now we plug and chug, right? We're going to take the 283.9, divide by the 141.94, and that's going to equal 2. We then take our empirical formula, multiply each subscript by 2, and that gives us, in this case, P4O10. All right. The empirical formula of hydrazine is NH2, and its molar mass is 32. What is its molecular formula? So there are your atomic masses, and here are your potential answers. So I'll give a pause here. So hopefully you came up with B, and here's how you should have done it. First thing we need is the molar mass of the NH2, and that's going to give us 16.017. Then we're going to take the known value 32, divide by 16. That gives us the multiplying factor of 2. We know that NH2 then is our empirical formula. We multiply by 2, and that's how we got the N2H4. All right, so we're going to end this segment here. The next thing we're going to look at is balanced chemical equations. And of course, this is going to be a useful tool for problem solving because now we're going to be able to predict how much reactants we're going to need for a reaction or how much product we should be able to make. Now remember, all atoms present in reactants must also be present among products. So coefficients are multipliers that are used to balance the equation. And so we'll get into that next and then see how stoichiometric values can help solve some of those equations as well.